The Institute of Physics and Mathematics of the Universe. And I hope your participation in this tremendous conference will be very helpful and very fruitful. And the first speaker today is Osamu Iyama from University of Cohen. Easy in now. Okay. It's still time for a little bit. Yeah, that's correct. So here is our speaker. And I first did geometry. So I have already introduced you. So we start our conference. Please. Thank you very much. Yes, probably yes. Okay, good morning, everybody. Let me start my talk today. Yes, so today I will talk about the Cohen-Macaulay representation of Saturn non-commutative analog of commutative Gorenstein ring called Artin-Schelter Gorenstein. Hope everyone can see this handwriting. And today I will concentrate on the case of dimension 1. And this is my joint work with Yuta Kimura and Kenta Ueda. Yes. So let me start with explaining what is Artin-Schelter
Gorenstein algebra. Maybe many of you already know. Yes. My setting today is slightly more general one. Yes, more general than usual one. Or many cases you saw before. Yes. So before talking about this, yes, let me talk something more general. What is Cohen-Macaulay representation? Okay, so now I consider an Italian league. And I don't assume A is commutative or non-commutative. Yes, A is non-commutative in general. And in this setting, there is an associated triangulated category called singularity category, SGA. This is sometimes often written as also DSG or some other symbol, but today I just simply denote by SGA. And this is by definition defined as Verdier quotient. So first we consider the bounded derived degree of finitely generated A modules. Then we consider the Verdier quotient of this triangulated category modulo perfect complexes. Perfect complexes are essentially, yes, complexes isomorphic to bounded complexes of finitely generated projective M. So please ask me if there is some terminology which I to explain or you need more explanation. So this is the so-called singularity category and introduced by Laguna Bookbach in last century, 1987, and also used by Orloff in the context of mirror symmetry. And today, yes, I talk about the Gorenstein ring, not necessarily commutative. This just means an Italian ring satisfying finiteness condition of homological invariant, important homological invariant given by the injective dimension of A as A mod. And we assume this is finite. And because I don't assume A is commutative, there are two dimensions, possible injective dimension on left-hand side and the right-hand side. And we assume both are finite. Yes. This is a definition of Gorenstein. Or sometimes this is also called the Iwanaga-Gorenstein ring in non-commutative set.
And A and the modulus over A are really modules.
Yeah, so this is as a left-on. Oh yes, this case mainly I used to say left-on.
Okay.
Yeah. Yes, but probably this doesn't matter anyway. So now for when A is Gorenstein, maybe I use this phrase also to say the graph. Place the Yes, then in this Gorenstein setting, we consider the category of Cohen-Macaulay module. Maximal Cohen-Macaulay module. It is defined as finitely generated A modules satisfying that there is no positive extension from X to A. Yeah, so this family of A module is very important and yes, studying commutative ring theory, representation theory, and also very important role in algebraic geometry. And one important property of this category is if A is Gorenstein, then this category is probabilis. This means that this category is closed under extensions in mod A, and moreover, this category has enough projective and also enough injective, and they coincide. Projective and injective coincide. So one of immediate consequence of being Frobenius category is that a stable category of A. Yeah, so this is just the quotient of this additive category, modulo ideal factoring through modulo ideal consisting of morphisms factoring through projective models. And this category forms a triangulated category, and this is equivalent to the singularity category as defined above. Yeah. So this is so yes. So therefore, the singularity category is very important in the context of Cohen-Macaulay representation theory to classify Cohen, to study, classify, and so on Cohen-Macaulay. Now, okay. Yes, today what I will talk about is a slight general modification of this category, namely Z-graded version of this category.
Excuse me, may I ask you, for this Gorenstein algebras, is it true that implies no complex A itself?
Oh yes, if A is Gorenstein, then it gives a duality, and vice versa. Yes. And now, yes, I'm talking about Z-graded analog of this. So now I consider Z A to B. I assume A is a Z-graded Cohen-Macaulay module, no, sorry, the Italian ring. And in this case, one can define Z-graded singularity category. This is by definition, yes. Just replace module category by the category of Z-graded A modules and the category of finitely generated projective A module by Z-graded finitely generated projective A. Then we get Z-graded singularity category. And also, yes, one can define Z-graded Cohen-Macaulay module just by using same vanishing point. Yes. In this case, if A is Gorenstein, then Z-graded Gorenstein, then we still have an equivalence between graded Cohen-Macaulay, stable category of graded Cohen-Macaulay module and graded singularity category. Then the problem the general problem we are interested in is the following. Namely, this is very easy to say. Namely, when does this category, okay, CMZA, when does this triangulated category have a so-called tilting object? Yeah. So let me remind you what is a tilting module. So for simplicity, I denote this category by T. So in general, if we have a triangulated category T and the object U in T, then it is called the tilting if it satisfies the following two conditions. Namely, first condition is yes. So this triangulated category has a suspension factor. Yes, I denote it by bracket 1. Yes. In the case of Cohen-Macaulay modules, this suspension factor is given by Kositegi factor. So taking co-kernel of injective envelope. Yeah. Then first condition of tilting object is home vanishing condition, X vanishing condition. So there is no home from U to U, shift by I for any non-zero integer I. So this is the first condition. And the second condition is generator condition. Yeah. So maybe let me write it. T is generated by U as a SIC subcategory. So SIC subcategory is a full triangulated subcategory of T closed under direct summons. So from U, we can construct all objects of T by taking mapping cone and suspension and inverse suspension and direct summand repeat. So this is a general flow. And yes, there are many known known results about this problem. For example, this category, stable category of graded Cohen-Macaulay module, has a tilting object in the following case. Yes. Well, first, let me state simplest case, namely A is finite dimensional and self-inject algebra. Okay. And yeah, so this case is known by Yamaura. In this case, always there is a tilting code. Yes, under the assumption that I should omit precise statement, but yes, A is non-negatively graded, and the degree 0 part of A has finite global. And these two conditions, this category always admit tilting. And also, classical case is
Sorry.
yes.
A was self-injective algebra, and this grading, arbitrary grading.
Arbitrary grading, just arbitrary grading, not necessarily radical grading. And second case I mentioned is a so-called simple singularity, or ADE singularity, and mainly in dimension 2 case. Yes. So simple singularity in dimension 2 has a natural Z grading, and with respect to it, this category admits a tilting. So this is the smallest known by Weigel lengthening for the last century. But yes, this was explicitly shown by in this century by Majimura, Saito, and Taka. And also, there are many other cases. For example, quotient singularity in arbitrary dimension, quotient and isolated singularity. Isolated quotient singularity case, there is always a tilting object. So this is my result is Ryo Takahashi. And also, many other cases. This type of results are known, but yes, today I omit this. Yeah. So, is it okay to write this phrase? I'm not very sure. It's only yes. Okay. So today, I will discuss the case of dimension 1. Somehow yes, rather complete answer. I will explain our setting later, but with respect to this setting, we give a complete answer. Yes, and our case is the case of dimension 1. So yeah, dimension 0 case, Yamaura's result shows that under these two mild conditions, they always admit tilting object. And we give this kind of result in dimension 1. So this is our goal. Yes. So yes, now now it is time to define what is Artin-Schelter Gorenstein. Yes. So now we consider a graded ring, non-negatively graded ring, and we assume that this is the Italian and K algebra, graded and graded K algebra. And we call this as a Artin-Schelter Gorenstein. dimension be first if the following conditions are satisfied. First condition is each degree I part of this ring cup is finite dimensional over L. So this is the first condition. And the second condition is just a Gorenstein. So to clarify, I write so again. So injective dimension on both sides are finite. Moreover, it's equal to D. They are equal. So this is the second condition. So just these two conditions are not very strong. We are just saying this is Gorenstein. But third condition is rather very strong. Namely, for any simple module S, and moreover, we assume that this is graded and concentrated in degree 0. And for consider such simple module, consider X group. So I to S to A. Then this X group behaves completely similarly as in the case of commutative case. Namely, if this is I is not equal to D, then this vanishes. In commutative setting, this means the depth of A is equal to D. No, yeah, this means A is Cohen-Macaulay. But we assume this condition for now, yes. And moreover, another condition is what happens for the case I equal to D. Yes. If I equal to D, we can regard, we can always regard this as a module over A opposite. So we are thinking left A module, but after taking home to X to A, then this becomes a right A module. And then this has a right A module. This is a simple again. So this is a simple A opposite module, and it is concentrated in 1 degree. And we denote the degree which is concentrated on by minus P. Degree. This degree is very important homological property, and I denote this degree by minus PS. So this minus is just by convention. Yes. And this PS is called Gorenstein parameter. And the quick remark is that classical case, in many cases, in the definition of Artin-Schelter Gorenstein ring, it is assumed that the degree 0 part is K. So many cases K0 is assumed to be K, but we don't assume this. Yeah. So this is therefore path algebra of quiver with a certain relation also can be Artin-Schelter Gorenstein. So this generalization is very essential.
If you assume it's Gorenstein, then 2 follows from 3, is it correct?
2 follows from 3. Yes, if we assume SNA is commutative or model finite over commutative ring, then certainly 3 implies 2. But unfortunately, it is not known in this setting that 3 implies 2.
Even if it's Gorenstein? I mean,
well, give me, sorry? What do you mean? Maybe I misunderstood your question.
Yeah, I mean, in this
speed. Definitely, it doesn't imply 3.
No, 3 implies
2. 3 implies 2 is very likely, yes.
If it's Gorenstein.
What do you mean? Gorenstein, okay. You mean,
because
yes, assume, okay, this is finite. Yes, I think so, yes. Certainly, if we assume 2, yes, injective dimension is finite, and condition 3 is satisfied, then condition 2 is also satisfied. This is okay. Yes, but without finiteness, it is an open question. One open question. Okay. So now let me, I think, yes, now Yes, we are talking issue right. Just to comment is so many important example of Artin-Schelter Gorenstein ring. For example, commutative n-graded Gorenstein ring satisfy this property. And moreover, yes, there are many examples given by so-called classical Gorenstein order, and also yes, by using Freeman with potential and its idempotent subalgebra, we can get many family of this. But it's just I already mentioned them, and now I should try to start with explaining our result. So is my talk 1 hour by the way? Yes, we study Z-graded singularity category for such. In the case D equal 1. And to explain our result, we need some notation. So assume D equal 1. And in this case, we define total quotient ring, graded version of total quotient ring as follows. Yes, which is we denote by Q is defined as a direct sum of morphism set in a certain category, abelian category Q grade. I write it now. And consider morphism from A to degree I shift of A. Direct sum of all of them. Yeah. Yes. Then what is this Q group A? So Q group A is a so-called cell construction. So it is defined by cell quotient of abelian category of G-graded M units. Model finite dimensional G-graded M modules. So model 0 A, 0 just means well, more yes, full dimension of module is 0, or yes, actual definition is a finite dimensional G-graded A modules. Dimension just means vector space dimension over K. Yes. So this is the cell quotient of abelian category. We get new abelian category. And we consider, yes, this morphism space and take direct sum. Then we have a canonical embedding from A to Q. And we call Q as a total quotient ring, graded total quotient ring, whatever. Yeah. Then we consider, yes, actually, yes, we consider certain modification of the category of Cohen-Macaulay module, which we denote by CMZ0A. Yes. And actually, this category, yes, let me first explain what it is. So, this is the full subcategory of G-graded Cohen-Macaulay module, satisfying the following property. Namely, oh yes, we are thinking left one. So consider Q tensor X over A. Then this has a structure of G-graded Q modules, and the condition is that this is projective as Q. Yes. Yeah. So yeah. So in the context of Cohen-Macaulay representation theory, yeah, this is nothing but so-called locally free over punctured spectrum. Yeah. Anyway, yeah. So this category has much nicer properties than just category of Cohen-Macaulay module. For example, this category admits so-called almost strict sequence or Auslander-like ends. So in particular, the stable category admits cell functor. Let me. Yes.
And you consider with T, right?
Q doesn't coincide with A. Q is much bigger than N. Yeah. One point is I assume D equal 1. If clear dimension or if depth of A is larger, then certainly Q constant with A. Yes, in dimension 1, they are quite different. Okay. And maybe one remark is this category admits sequence, and the other remark is that okay, again, this category has a structure of Frobenius category. Therefore, the stable category has a structure of triangulated category. And moreover, this category meets same factor given by given by tensoring with certain A by omega. Omega can be constructed by using local cohomology. Yes, but I omit some detail. So this category behave much nicer than CM, just Cohen-Macaulay module, and I will discuss existence of tilting object in this category instead of just Cohen-Macaulay. Yes. So now, yes, notation. Yes. So, as I go, we consider AS. AS is just Artin-Schelter to save time. So now A is Artin-Schelter Gorenstein algebra of dimension 1. And moreover, we need a little bit more parameterization. Yeah. Namely, in general, because we don't assume degree 0 but is K. So in general, there are many simple A modules on which are concentrated degree 0. But they are only finitely many. And we denote them by S1 to S. So S1 to Sn. So they are all simple A module, simple A modules concentrated in degree 0. Yes, always, yes, under this assumption, finiteness assumption, there are only finitely many simple A module concentrated in degree 0. And I denote by their Gorenstein parameters by P1 to Pk. Remember that the Gorenstein parameter just means, yes, the degree such that equals to D from Si to A concentrate on. Okay. Yes. So, and yes, then maybe in this, under this terminology, the following holds. Namely, there exists permutation of 1 to n, satisfying the following isomorphism. Namely, our case D equal 1, so we consider first extension from Si to A. Then this is a simple A opposite module and applying K duality. Yes, so D is the K dual. Then applying K dual, this is again simple graded A module. Then and it's concentrated in some degree. Yes, degree minus Pi. Therefore, we have so this is some simple module. So yes, and I denote this index by new of yes, and by this condition, this is concentrated related in degree EI. Yes. So yes, we can always get such permutation here. This is by definition. Okay. And under this terminology, then we are ready to state our next level. Yes, maybe so far there is no any question. Maybe I got example. Example, yes. I see, yeah, you can give example, yes. State theorem first or state example now? Maybe state theorem first. Yeah. Yes, immediately after theorem, I will give. Yes, so under this assumption, moreover, we assume that the global dimension of degree 0 path is finite. So this is somehow last additional assumption. Yes, we assume non-negatively graded, and yes, these three conditions. Yes, for assumption of these three conditions, and degree 0 path has finite global dimension. So this is very natural condition. For example, classical case A0 equal K satisfy this condition. And this case, our first statement is that the stable category of Cohen-Macaulay module which are locally free of punctured spectrum has always shielding object. Yes. This does not necessarily have a tilting object, but always admits a tilting object, shielding object. Yes. Yes. I regret I forgot to define what is shielding object. Yes. Yes. Shielding object is yes. Basically, almost the same definition. Remember that tilting object. So I denote this category by T. Then tilting object is defined by first condition is X vanishing condition, which is not all integer I, which is not equal to Z. This was the tilting object. So this was the definition of tilting object, but tilting object satisfy weaker condition that yes. So extension group vanish for all positive. So there could be negative extension. This is a yes. This is the difference. And we assume also same generating condition. Namely, T is generated by V as the 6 subcategory. So this is completely same, but only difference is I is restricted to positive integer. And yes, but this is a weaker version of tilting object, but it turns out recent development in tilting theory that such generalization of tilting object is very essential and have to be considered. Yeah, especially in the context of mutation. Yeah. Anyway, and this tilting object can be described. Okay, can be written very explicitly as follows. Actually, this construction is extremely simple. Namely, first we consider degree shift of A by I. Yes. And consider I equal 1 to some large integer n. And this is just a free module, projective module. So this is 0 in stable category. But we truncate, yes, and throw away the negative degrees. So this is actually submodule of free module AI, but this itself is, of course, not free usually. So in this way, we get shielding. And yes, so this V is, so if n is enough large, then this V is always gives us a shielding. And if we take n larger and larger, then yes, so this V has more and more direct summand, but yes, essentially, yes, at some point it stabilizes in the sense that we don't get a new direct summand. This is because of A has dimension 1. So this is we get shielding. And moreover, we have a simple criterion for sufficient conditions that this V is a tilting object. So this V is actually a tilting object. If the following homological condition is satisfied. Namely, yes, our Gorenstein parameter P1 to Pn, all of these homological invariants are non-positive. Yes. So yes, just if these parameters are non-positive, then this will give a tilting. And the second statement, so this first condition gives the first statement gives us explicit tilting or tilting object. And the second condition gives us explicit criterion for existence of tilting object. So our triangulated category has a tilting object if and only if one of the following two conditions are satisfied. Yes. So, okay. So either, yes, first case is A is regular. Artin-Schelter regular. Just this means global dimension of A is finite. Yes. Yeah, actually, Artin-Schelter regular algebras are, well, more classical notions than Artin-Schelter Gorenstein. And in that case, state singularity category is 0, and this category is also 0. So 0 category and with the tilting of 0. Yeah, so this is very not interesting case. And the interesting case is the second one, namely certain homological invariant, which I denote by PA, is non-positive. Yes. And this PA is defined as follows. Namely, yeah, this is not very difficult. This is just average of all Gorenstein parameter P1 to Pn. So this is just a sum from P1 to Pn and divided by n. Yes. And this value is non-positive. This characterizes existence of tilting. Oh yes, I forgot one condition. So ring in the composition. So assume that we need to assume that n is indecomposable as a ring. Yes. But of course, yeah, ring indecomposability is not, yeah, very mild condition because we can always decompose it ring indecomposable summands. Then this category also becomes the product of same category for each sum. So assuming ring indecomposable is almost, yeah, obvious.
Excuse me, in the first statement, yes, here, this V is tilting object when and there is capital M.
Oh yes, we have yes, we can describe an explicit. Yes, but yes, there's no explicit formula for n being smallest possible n.
Just yes, about the statement. So if it's tilting for n big enough, and this for when it's tilting, it becomes tilting. That's what you mean. When it's generating, then it becomes tilting. This PIs are also it.
Well, if yes, so for SMA, so this is the tilting for certain n, and for that n, V is tilting if this condition is satisfied. So this is our main statement, and in the rest of my talk, I will explain the example of this statement. So I think if you have any questions, please just me now.
Yeah. All A are infinite dimensional. So A cannot be finite dimensional. Unless D is 0 properly.
Yeah. D equals 0 place A is.
In other cases, it cannot be.
Always it's D is larger than 1, then A is always infinite. This is this follows the problem. Home vanishing from simple to A. Okay, so let's then give some so yes. Which one should we use? Yes, yes. There is a general construction of Artin-Schelter Gorenstein algebra. Namely, here is the field is binomial for the variables. So this is just a point. And assume that it's an so-called R order. Okay, maybe Gorenstein. Yeah, this just means that A is an R algebra. And moreover, A regarded as R module is free of finite. And moreover, Gorenstein just means that painting R dual of A and regard this as A module, then this is projective. Projective as A. So R algebra satisfying such condition is called R order, and the second condition is also satisfied, then it is called the Gorenstein order. Yeah. And if A is Gorenstein R order, and moreover, A is Z plane. If we have a Z degree on R, such that each degree is positive, and moreover, A has Z grading compatible with Z grading on. Then, yeah, such A is Artin-Schelter Gorenstein. Well, yeah, maybe this is some two general recipe to construct AS Gorenstein algebra, but certainly provides us many examples. Maybe one remark in this case is that Z-graded Cohen-Macaulay module is nothing but Z-graded A module, which are projective as R module, or free over R. So this is A module, which is projective over R, just Cohen-Macaulay. Yeah, this is just remark. And yes, I will give a more concrete example. Yeah, this is probably too abstract. And it's actually some Cohen-Macaulay representation. Such order well studied in representation theory from last century by school of Auslander and also Droita, Kirichenko in Ukrainian school. Yes, and one of well-studied class of order is so-called tiled order. And yes, this is mainly in the case T equal 1, even though we can define higher limit version. So now R is just a polynomial ring of one variable, and for simplicity, degree of x equal 1. And we consider subring of n by n matrix ring over A. And this subring has well, very well tiled, nice shape to describe tiled. Namely, the ij entry of A is given by power of maximal ideal of M of R. M is just principal ideal generated by X. Yes. And ij is just non-integer, or for simplicity, I assume non-negative integer. And yes, of course, it depends on choice of these integer aij so that a becomes a ring. But we assume that yes, simple numerical criterion implies that A actually forms a subring of MNR. And also, it is not very difficult to describe when this A, okay. This A is by definition R order. Yes. This is a free R module of rank n squared. Therefore, this is R order. As an R module, this is free of rank n squared. And moreover, if we Aij is chosen, Aij plus Aj is bigger than or equal to K. Actually, this is the condition. This forms a link. Yeah, it is very easy. So, yeah, and yes, in this case, this has a structure. This is an order, and it is also not very difficult to characterize when this becomes a Gorenstein, but I omit it. And instead, I just give a simple example. So, for example, yes, R itself is too simple. So instead of such tiled order. So this is a 2 by 2 ring, and yes, we assume A is positive, strictly positive. Yes. Then this is the Gorenstein R order. Well, simplest of examples. And yes, let me state general statement result. If so, maybe I should state as follows. So there's not any type. Then for any tiled order A, there exists certain partially ordered set, which can be described explicitly. Yes, but I think just to show example. And satisfying the following property, namely, yes. Actually, in this case, we don't need to consider 0 here. Yes. Actually, in this case, 2 categories are the same. Yes.
Doesn't mean that Q is the same as A.
Yes, no, Q is in this case, Q is actually n by n matrix ring over Laurent polynomial. Yes, this shows some idea. Yes. Right. So the graded total quotient ring is just a full matrix ring over Laurent polynomial. Yes, and therefore, yes. So this is the principal ideal domain. So any graded module is projective. Yes. So this 0 condition is automatic. This is just one. And the statement is that this triangulated category is equivalent to the perfect derived category over the incidence algebra of I. So for each poset I, we can associate a finite dimensional algebra. Okay, this is actually finite poset. So instance algebra is finite dimensional, and yes, we can associate this finite dimensional instance algebra. So yeah, this is a follow. Actually, yes, in this case, the condition of Gorenstein parameters, yes, so mostly almost satisfied, automatically satisfied. We get this feeling. Oh yes, this is perfect complexity. So maybe we can also write a JD project. Yes. Yeah. Homotopy category of regenerate.
It is the same as here.
Yes, instance algebra has a finite global dimension, so it is possible to write down that this is finite bounded derived category of finitely generated KI. This is yes possible. But the reason I use a perfect derived category is that maybe I didn't explain this, so it's good time to talk about this. So if T is triangulated correctly, and we have a tilting object, then under mild or under, yes, if this T is a reasonable triangulated category in the sense that it has an enhancement by DG category, such triangulated category is called algebras, then such a triangulated category is equivalent to the perfect derived category of endomorphism link over tilting object. So there is a general statement like this. Therefore, I prefer to use the perfect derived category, the bounded. Yeah. Anyway, yes. So this general corollary tells us that there is a tilting object, and we have yes for tiled order case. And let me show you. Yes, actually, what is a poset in this case? And yes, yeah, actually, describing poset is too simple, but yes, for some people using Gauss-Lambda quiver gives you some more idea. So actually, we can draw so-called Gauss-Lambda quiver of the category of G-graded Cohen-Macaulay A module. This is very classically known in Cohen-Macaulay representation theory, and I denote by pair Ij, the module. Yes, by some reason I use light module here. Yes, this is just because of time difference. Only here, sorry for this. It doesn't matter. And yes, so this is a low vector, and so the ring A. Okay, now A is just this. So this ring A acts from right hand side. If I and J satisfy the following inequality. So I minus J is belong to the interval between minus A and A. Then this low vector gives us a Cohen-Macaulay module. A module which is graded Cohen. Yes. And using this symbol, we can describe the Gauss-Lambda quiver of this category as follows. So we have a yes, AR quiver general shape of Gauss-Lambda quiver is like this. So we have a mesh. So we have a projective module in top side and bottom side, and yes, each vertex is indecomposable of Cohen-Macaulay, G-graded Cohen-Macaulay A module, and each arrow is gives us a special morphism called irreducible morphism. Yeah, it is actually a basic unit of the structure of additive category CMZA. Yeah, whatever. Then Gauss-Lambda quiver have a shape 0A is here. No, yes, and then 0A minus 1 is here. And we also have a 0 is here, and A minus 1 0 is here, and so on. Yes. So we have a yes, so this structure is very well known in the representation theory. And yes, we have a module which is 0, 0. And actually, just look at this full sum quiver. Yes, this full sum quiver has a V shape. Yes. And yes, actually, this has natural poset. Yeah. Those are inclusion of modules. So yes, so this can be regarded as a poset, and this regarded as a poset is gives us I, which appear in the corollary. And this I is yes, just yes. In this case, maybe yes, I write here. So in this case, Ki is incidence algebra is actually nothing but okay. Maybe let me say one more thing. Yeah. Actually, everything appear in top and the bottom is projective. Yes. So they become zero in the singularity category. So the Artin-Schelter equivalent of singularity category can be obtained by deleting top row and bottom row. We get AR equivalent of the stable. And now, yes, if we drop two vertices, then well, how many vertices? 2a minus 1 vertices. Yes. If we drop these two vertices, then there are 2a minus 1 vertices. So yes, so this incidence algebra is nothing but path algebra of thinking quiver of type A with 2a minus 1 vertices. Yeah. So in this case, the stable category is derived equivalent to thinking quiver of type A. Yeah. And actually, yes, we can give many, well, yes, applying our theorem, we can obtain tilting objects very easily. And yes, if A is enough simple, in the sense that maybe I should delete somewhere to look on this thing, or yes. So actually, yes, so if A is a simple singularity in dimension 1, so this is an ADE singularity. Yes, in this case, also there is some canonical Z grading on A, and trying our theorem, one can conclude that the singularity category is equivalent to the perfect derived category of thinking quiver Q. And this thinking type mostly coincides with the type of singularity of A, but there are small differences, which I don't say. No. And this observation, okay. Yes, using our method, yes. Actually, this kind of observation was more or less known by Dietrich and Wiedemann, for example, in last century. But yes, we give another proof of this equivalence by using our main theorem. Yeah. Using this theorem, we can easily get. Sorry, yes, this is commutative. Simple singularity, in my sense, is commutative. And actually, this commutative case was not originally in, yes, this was in my joint work, previous joint work with Laguna Hukbalitz, self and Yamamura. In this joint work, we discuss commutative Gorenstein ring of full dimension 1. And what I talk today is non-commutative generalization of my previous joint work with Laguna and Yamamura. Yeah. Anyway, so this is the answer example. Maybe I have 2 minutes, so just last example. Technique example. Yeah. Unless you have any question, there will be time for questions. So this example is so-called the non-commutative quadrics. Quadric hyperspheres. Yes, actually, our result is for Artin-Schelter Gorenstein ring of dimension 1, but it has application to Artin-Schelter Gorenstein ring of higher dimension. But we need to assume that they are hyperspheres. Actually, non-commutative quadric hypersurface is defined as quotient of S by principal ideal F, where S is Artin-Schelter regular. Artin-Schelter regular is, as I already mentioned, just replace inject finiteness of injective dimension of ring. We assume that finiteness of global dimension. And we assume degree 0 is K. So, sorry, Artin-Schelter. Yes, not Artin-Schelter regular algebra whose degree of half is 10. And F is certain, yes, regular and normal element. Normal and element in degree 2. Yes, so F belongs to degree 2. And in this case, actually, we can apply our result, not B, but instead of we can apply our result to the quadratic dual of E. Yes, well, it's opposite. Applying quadratic dual or cosine dual, in other words. So actually, cosine dual of B gives us the AS Gorenstein algebra of dimension 1. And we can apply our result. And actually, cosine duality gives us equivalence for duality between our graded Cohen-Macaulay module and bounded derived category of cell construction tubular of B. And therefore, our tilting object gives us tilting object in tubular of B. Yeah. Sorry, yes, no, it's over. Thank you for your time.
Questions, please.
Something you can in particular apply to the commutative case, right? You don't know what you will get. Will you get from filtering object with a inner bundles or something? Yeah, from the
Yes, it's yeah, actually, there's an explicit construction in of V, and yes, actually, yes, one can specialize this tilting object to the case of classical commutative quadratic hypersurface, and yes, actually, we get Kaplan of the tilting using spinor.
And in general, do you have a full exceptional collection or?
Yeah, yes, actually, yes, it gives, yes, so this is connected, yes, and the connected case we get exceptional collection, yes. Tilting in undefined assumption also gives us exceptional collection, full exceptional collection. Under the assumption that I think is the quiver of A0 is acyclic. Yes. Just this acyclicity, I think, gives us full exception.
Okay, questions, please. If not, let's thank the speaker again. And we resume at 11:30. So we can break.
What's misunderstood as a weak mathematics? That's what's I said it was like.
いや、まさに、逆に東京に行っちゃった。
住んでるんです。
東京、名古屋のセミナーの案内とか100万円。ぜひ。最近だけどね、全部フォローできなかったよ。あ、こういう感じ、こういう感じってない。最近のそういう時、最後に割るのは両倍ではする。
これは、ノーマルという条件を仮定してて、それは 左、F で生成される左であるが、右であるにもなってる。そういう条件。
何が
それをノーマルって呼ぶんです。いや、私はこれは上山さんの担当した箇所なので、彼の用語だ。というか、この分野では使われている用語です。非可感代積は。
今 F を取ってくる。
はいはい。
それで、とにかく強引に左でやるんですけど、それが自動的に右。
それを仮定するんです。
する。
ね、仮定なんですよ。だから、
じゃあ、それは F に対すると。
F に対する F と S に対する仮定。
両方。
はい、はい、そうです。で、F は S のデグリー2次の正次元だってことも確認してるんです。S2 って最後書いて。すいません、なんか最後、非常に
駆け足が、ちょっと
最初の受けつかないが。
こういうところで徹底的にやると。
上山さんとかをもっと徹底的にやってます。例えば S として普通の多項式間を考える以外に、x かける y がマイナス yx っていう、そういうひねったような関係式を許したようなものを考えて、
出てこないです
ね、
コントキュージレーション、xy、yx イコール。
そうです。そういうのは AS レギュラーアルジェブラのクラスとしてよく調べられていて、コンタムポリノミアルアルジェブラと呼ばれるものの特別な、呼ばれてはいます。その場合に、ティルティングがどういうものにするかとか、そういうのをかなりエクスプレシットに上山さんは調べていて、グラフの組み合わせに認識されるという結果があります。
完全に台数の方に行っちゃってる。
これはまず S です。
いや、実はね、ティルティングっていうのは、その科学の立場だからね、そうすると、リアルでね、今の方程式 F があると、F イコール0とか F イコール1という面があって、それにホモロジークラスですね。それで、そのホモロジークラスをどう生成するかっていう問題式と、いろいろ関係している。だから、そっちの方の
それなんかファイバーとかそういうお話ですか。
だから、前にいろいろと、このティルティングという概念とはどう関係に。
斉藤先生、今日お話しされる。
今日もティルティングは触れないと、一挙に文系だね。
お話、オンラインです。そうなんです。
自分の配信してる。
安心してます。
ちょっと、入れてみたいな。
近いとこいて。